Alright, so let's talk about rotational motion. Now, rotational motion deals with how an angle is affected, whereas linear motion, or kinematic motion, deals with how distance is affected. So let's take a look at this. So starting here, we have just an object at rest, but when the object is rotated by a little bit, essentially there is an angle that it's been affected by. And the angular displacement, so the angle from here to there, is given by theta. So yeah, theta is an important part of rotational motion, the angular displacement, the change from the initial angle to the final angle. And likewise, the angular displacement can be changing just like how distance is changing with the velocity. So angular velocity, or omega, is how the angular displacement changes over time. And also there is an alpha, which is the angular acceleration, so how this rate changes over time. And yeah, that's rotational motion. And rotational motion can be linked with linear motion through the radius. So multiplying each of these objects by the radius can give us the linear components. So r times angular displacement gives us the distance, or more specifically the arc length. R times the angular velocity gives us the linear velocity, and r times the angular acceleration gives us the linear acceleration. And just like kinematic motion, rotational motion is also defined by kinematic equations. Alright, so here are the rotational motion kinematic equations. As you can see, they are very similar to the normal kinematic equations. It's just that distance is replaced by angular displacement, and velocity and acceleration are replaced by their angular counterparts. And yeah, these are the equations that we use to solve rotational motion problems. Alright, so using our knowledge of rotational motion and the 5 kinematic equations, let's go ahead and solve this problem. So 4 children climb on a carousel that is initially at rest. If the carousel accelerates to 0.4 radians per second within 10 seconds, what is the angular acceleration? What is its linear rotation? 3 meters from the axis of rotation. Alright, so we are given the initial angular velocity because it's at rest, so Wi equals 0. And we're also given the final angular acceleration, which is 0.4. And we're given the time of 10 seconds. And we're asked to solve for the angular acceleration. Oh yeah, and also the normal acceleration. So based on the givens and what we're asked to solve for, we would use the final angular velocity is equal to the initial angular velocity plus the angular acceleration times time. And rearranging this for the angular acceleration, we would get the final angular velocity minus the initial angular velocity over time, which would be 0.4 minus 0 over 10, which equals to 0.04 radians per second squared. And that is the angular acceleration, but it also asks for the linear acceleration 3 meters away from the axis. So we just multiply the radius by the angular acceleration, so that would be 3 times 0.04, which gives us 0.12 meters per second squared.